So let's start. Uh, Today the tutorial is going to be about um, first we'll talk about L1 L2 optimization, basically how to solve the relaxed sparse coding problem, and then we'll talk about BM3D. It's yet another denoising algorithm, but a very well performing one. So the agenda is like this. So we'll talk first about L1 L2 problem. We'll get to this problem from the inverse problem setting, and we'll talk first about what sparse coding is and define what L1 L2 is and propose an algorithm to solve it. And we'll also discuss another greedy way which is not taught in the class to solve the L0 L2 problem. And yeah, we'll discuss one acceleration scheme, one simple acceleration scheme, how can we accelerate the convergence of ISTA, and then we'll see how to implement it on a toy problem, and we'll talk about BM3D then. So yeah, to bring us on the same page, so we're majorly interested in these kind of problems where y is our measurements that we get, and we want to recover x, which is the latent signal. So we assume that most of the deformations in image processing, like focal blur or motion blur or missing values, and projections in CT, like when we discussed in the third tutorial. So all of these, so basically that's what we get in Y after going through all these deformations. And our goal is to recover X, and accordingly we rename what we do, just depending on this D. So if we are removing focal blur, then it's super resolution. If you're removing motion blur, then it's deblurring. Essentially, everything is of the same mathematical form. Y is equal to dx plus n. And today especially we want so today we're interested in the following thing. Like we want to represent, let's say this dictionary, D is a dictionary. We call it a dictionary, and it is a set of atoms. Today's focus is that X. We want to represent Y as a linear combination of atoms in. By atoms, I mean the columns, right? So columns in D, and X represents how much contribution are you going to give to each column, right? So our problem is just this, but it can also be, it is very general, and it can be applied to all these tasks. And see that if it's an identity, then it's basically a denoising problem. You're just adding noise to your forward model, and you want to remove it, right? So our goal today is to find such an X which reconstructs Y using this dictionary D by only using a very few number of atoms, right? So how do we formulate this? Let's say Y is our signal. You can think of it as a signal, and D is our dictionary matrix, where you are building these kind of things. One example of D can be, let's say, what we already know, the Fourier dictionary. Let's say you have a Fourier in your dictionary D. So basically you have to use all your, we saw in Wiener filter that we can cut off at a certain frequency, and you can reconstruct the whole signal faithfully without losing much, right? Or you can think of it as a DCT dictionary, and today we'll think of it as a redundant dictionary, where you have a lot of columns, but relatively less number of rows. So now we want X to be sparse. Like you have it has to choose from a very large set of all the possibilities, which in a sparse way, how to reconstruct Y, right? So we can mathematically formulate it as follows. We want to minimize the number of entries in X. We want to minimize the number of entries in X, which we can get from the L0 norm, and such that we have a faithful reconstruction of the signal, so such that your Y doesn't have any funny things in it. Okay, so and you assume that our dictionary is capable of providing you the variability. Like you're not learning the dictionary like what Alex taught today. We have a fixed dictionary. We want just X, just the first step, right? So we can solve this. So this is basically a constrained optimization problem. We form the Lagrange multiplier lambda, and we write it as an unconstrained problem, and this can be solved. This is a very tough problem, and because because it is NP hard, because as x grows, the number of possible solutions grows exponentially. So it's an NP hard problem, and it's very tough to solve. So we'll discuss one way how to solve it greedily, which doesn't have any guarantees if your x is not sparse enough. If your x is sparse enough, then you can there are guarantees that you can recover. You are recovering the correct thing, like your x is recovered properly if x is sparse enough. But so one simple way is, like anybody would think of, how would you do this? How would you solve this problem in a greedy way? You just initialize some support. You have you want to basically you're putting in your bag all the which elements in D to use, right? So you want to first choose. So first you go to the first row in the dictionary, you ask it, then you check all the rows in the dictionary if which one gives you the least error. That's what we call as residual, which initially we initialize the residual with y. So you're picking the first atom in the dictionary. By atom I mean column. So we want to choose the first atom in the dictionary which minimizes the error, right? So you put that, and then you recalculate the residual. So you have a new residual. Now you want to pick the second atom in a way that minimizes this residual. So and so on. You have a fixed limit of sparsity. Let's say you want to pick only 20 atoms. You do the same procedure 20 times. Like you pick the first atom, then update your residual, pick the second atom, update the residual, and so on. So at the end, you will end up with 20 greedy atoms. Like some atoms might not have gone together, but since you were picking it in a greedy way, so you first made a pick, so you can't remove it. So you are basically recovering the support. By support I mean what atoms to use to reconstruct Y, using such greedy methods. So this is a greedy scheme, of course, and but it is guaranteed to recover the signal faithfully if x is sparse enough. Like if inherently your signal is sparse enough, then you can use this, and you will be able to recover it completely. There are some bounds which I mean you can read Mickey Ladd's book on they define some bounds on how much sparsity should it be so that you recover the signal faithfully. They define it using some mutual coherence criteria and things like that. But you can read more about it in Mickey's book. So now instead of so we don't want to use such. So here we are defining some kind of an approximation. Like you're not asking y to be exactly as dx, right? You're defining it some error and you want to minimize that. So now since this L0 norm is ugly and it doesn't let you differentiate through it, you want to relax it in a most faithful way so that the problem still remains the same, and you want to solve this problem to get to the sparsest solution, right? So one way to relax it is, of course, change this L0 to L1. So this is now this problem is convex, right? I mean, except it's convex, but it's not smooth. So it has a so now we know some ways how to solve this. So we'll discuss one way. Like Alex derived one of iterative soft thresholding in the class. We'll briefly go over the proof and we'll see what the update scheme is, and we'll implement it. Okay. So yeah. So now since we converted our highly non-convex problem into a convex one, now we can solve this to get an estimate of x, right? So we can solve it using basis pursuit, which is proposed by proposed in the 90s, and the another way is ISTA, but ISTA is more general and you can immediately connect it to neural networks. So we're discussing in this course we focus on ISTA, and we'll also see one simple acceleration method called FISTA, which is just fast ISTA, and what goes on there, right? So right now, since I took the slide from Alex, so we'll call our dictionary as phi and our signal as c. Signal, I mean our latent signal, the one which we want to recover. So now, since we have such an expression, we can just write it as as a d transpose d thing, and you want, when we can expand that, and since we are minimizing over the signal which is c and x, so we can get rid of this term in gray, and we will end up with something like this. So this is a combination of smooth term and a non-smooth term. Now you want to in the literature it's very well studied how to optimize such a smooth plus non-smooth convex functions. So one of the ways is the fixed point method, which Alex discussed, but there are also other ways to do it. So essentially, when I want to just clarify a few things if it might be confusing. So Alex says you want to fix C and you want to approximate the G of C around it, right? By G I mean the smooth part of your objective function. So by that you mean if your function is something like this, you want to minimize over the green thing, you want to reach the minimum there, and then you want to project it back to your original function and then do it iteratively, so that at one stage you will end up with this point, right? That's our goal. So since we expand it around C, then we can write it this way, and n is the curvature of which is basically this point. When you derive it twice, you get the curvature. So n is eta is basically the curvature, 1 by eta. So and so on. We can write it like this, and if we take this term as an if we by simple replacement of variables, so you can write it as z, then basically you're converting, since this is everything is separable, you can instead of solving this problem, you can just solve n one-dimensional problems, which is easier because you can parallelize it. So and then you get such an equation, and since now we know the gradient of what this should be of the continuous term. Again, red is non-smooth. By green I mean the smooth one. So now if you don't have a differential, if some function doesn't have a is non-smooth, then you can basically define a sub-differential set, which is basically here u is discontinuous at again I'm saying is continuous, it's non-smooth, is non-smooth at u is not equal to 0, it's smooth elsewhere, and it's non-smooth, so you can define anything between -1 and 1 when it's equal to 0. So this is your sub-differential set, and now in order for this to be optimal, so you want to this is basically the Lagrange condition, like you have your delta g of x plus a delta of what do you call it, delta of h of x, both of them together, the sum should be equal to 0. So when you replace it, we end up with a shrinkage operator. This is basically we can be denoted by s mu of z. You've seen all of these in the class. I'm just recalling. So yeah, so basically our ISTA, at the end we end up with the following thing. First you take a gradient step over this where do you have the problem? First you take a gradient step over this objective function, and then you do a shrinkage, so accounting for this one. By shrinkage I mean you do just a thresholding. If it's between minus mu to mu, you replace it with 0. If it's above mu and below minus mu, you replace it with x minus mu, or minus of mod of x minus u, right? So that's what we end up with. So the update scheme is like this. So essentially you get your input y. So now so initially you initialize with some x equal to 0, let's say, and your update scheme is the following. So by start it's the transpose, xk is minus nd of nd transpose times this thing, which goes to a shrinkage operator, and then it happens over and over again, right? So I wrote it this way because I want to use it in the next lecture. So basically one thing what was proposed in 2010 was basically this looks like a neural network, right? Basically this is your weight matrix, and this is your input, and this is your ReLU, right? So I mean this is not your ReLU. it's just if you make it non-negative, then it's a value. So essentially, this is equal to solving. I mean, this is equivalent to solving a multi-layer neural network. That they did it, and they just tiled one after the other, and then they said, okay, let's forget about what this is. We have such a structured network. Now we will just define this as weights of the network, and we'll learn through using stochastic gradient descent. And the result is, it's very surprising that if you stack 20 such layers, it's equivalent to running this loop 1,000 times, which just accelerated the whole thing like 50 times, right? So that's one interesting thing. We'll also see that in the future lectures. And so one fast variant of this is you can use the history. You can save the xk minus 1, and you can define what weight do you want to give to this direction, and the weight is defined by this. So it's called it's some ratio. They have this ratio will further relate to the convergence rate, which I'm not going into. You can refer to this paper. Basically, you just update your scheme using like this, and it's called FISTA. Basically, it's just a very small modification. You're just keeping a history xk minus 1, and you're also giving a weight to that direction from xk to xk minus 1. So, and then and then you do the same thing over and over. So now we'll see a very simple code on how to program this. I'm just defining this. I'm defining d to be random, and I'm giving some x, which is inherently sparse, and I'm calculating. Basically, I know the x, which is sparse, and I'm multiplying it with a random matrix, and I'm getting the observation y. Now, when given y, I want to reconstruct back x, right? So this is exactly compressed sensing, which Alex will teach in the next class. So I'm creating a matrix of size 15 by 20. This is the random matrix, and I'm creating a sparse signal. Basically, I'm taking this random matrix and I'm cutting down whatever is below 0.8 and putting it and removing everything else. So essentially, you have a sparse signal, which and then my ISTA goes like this. It's pretty simple. So you're creating a space for your sparse signal, and you're calculating the. So yeah, one thing I forgot to mention was this eta. This eta, which we brought up with it. The convergence heavily depends on what the choice of this eta is when you're solving this when you're solving this problem. So basically, if you choose your eta to be, if you choose your lambda to be less than 1 by 2 eta, then only then it will converge. Otherwise, it won't converge. So that's one choice. So and then first I want to soft threshold the following thing, which is A transpose B minus AX. Basically, it's the same as this. A transpose, I'm subtracting and putting an addition here. So this is basically this equation, and then this is to account for the convergence, the L thing, and then I'm just doing it over and over again, right? So in the case of FISTA, I'm just defining my initial t to be 1. My initial t to be 1, t0 equal to 1, and then I'm also keeping in mind what was my previous direction, and I'm I'm giving weight to that, and I'm adding it in this x hole, right? So that's it, and now and then I'm comparing both. Show you how the signal looks like. So originally this was my signal, which was sparse, and I'm multiplying it with a random matrix of A. So essentially, this is what my ISTA was recovering. Wait, yeah, this was what my ISTA was recovering, and this is what my FISTA was recovering. Both were good, but you see some flaws here that it was supposed to be 0, and it gave some value, so it's not perfect, but. Yeah, so you see the convergence is better for FISTA because of this additional history direction, And if you increase this is just a toy problem, so you can just increase the dimensions of your array. And so here you have, I mean, since my matrix is 200 now, my signal is 200 and I'm cutting everything above 0.8, so it's sufficiently dense. So now ISTA was completely messing it up, but FISTA was quite faithful. You can see the same thing in the convergence rate, and this additional history direction that you added was it helped it converge sooner. So one more thing about this history direction is it's exactly the same trick as what is called as a Nestor's momentum that you use in neural networks. It's exactly the same trick. Just Nestor proposed it in 1985, and these guys are using it now. So so yeah, that's ISTA and FISTA. I didn't implement OMP, but that's also pretty simple. You can just recover. So anyone has any questions until here? Is anything not clear? I'm going to BM3D. So okay. So yeah, so we'll talk about image denoising. So until now we saw a few algorithms how to denoise images. One was non-local means, bilateral filter. Bilateral filter was doing pixel-wise. Non-local mean was looking at patches but still doing pixel-wise. And Wiener filter was using just Fourier transform and cutting off what was not needed in a smart way. So BM3D is a combination of both spatial and also frequency and transform domain. Calling it transform domain because I'm not going to use F50 now. So basically, F50 is also a transform, Fourier transform. Yeah. So it's not really frequency domain, but some transform domain filters. So there are three key ideas in BM3D where they basically they match. So when you're given a noisy image, they choose patch, they go to every patch, and then they see all the similar patches across the image, and then they want to denoise all this group together. So they will tile them up, and I'll show you some nice pictures. So and then they get estimates of each denoised patch in every in all these tiles that they call. So basically you have an image, you choose all these patches, R is your reference patch, and you're choosing whatever is closer to you, and then they will group them all into a file, and then they into a tile, and then they apply a 3D transform. 3D transform can be DCT. I'll explain what DCT is, and then they do some hard thresholding in the DCT domain, and then they get and then they do the inverse DCT transform, and they get a denoised group of patches, and then they distribute wherever they came from, right? So yeah, I mean, basically, how do you do this block matching? So you go to let's say my reference patches this red patch, and I go to all these blue patches, and then I see if it's less than some threshold. Since one thing to keep in mind is since we have noisy blocks in the noisy image, so you have to set your threshold to be a little higher. And then if it matches the threshold, then you just add it to your group, and you build up a tile of patches. So basically, then you apply, then you treat this all these patches like, think of it like a video, and then you apply a 3D transform and not a 2D transform. For example, this image, if you apply 2D DCT transform, I'll tell you what it is. But if you apply 2D DCT transform and then cut off all the I do an iterative hard thresholding, then you get something like this. And basically, the sparsity induced is alpha. So how many atoms are you keeping is basically the number of amount of sparsity induced, right? And if you want to denoise several such patches, then basically you can do it in patch wise, which will essentially mean like you're inducing k alpha sparsity, like you're inducing k alpha sparsity for every patch. But instead, what BM3 proposed is, okay, you tile them up and build a cube, and you apply a 3D transform instead of 2D, so that they will also be using information from the other patches which were similar to it. So you'll essentially get alpha. I mean, you're trying to induce alpha sparsity on all the similar patches, taken from every patch location, right? So yeah, the question is now why not why do it in DCT and why not do it in Fourier transform or let's say the wavelets, right? So if you see, so this plot basically tells you how much it's in log scale, the x-axis and also the y-axis. So how much information is captured by when you're cutting down information. If you see a 50, the blue line, so essentially when you're cutting, it's not damping fast, which means that there's significant information even in these regions. But if you see DCT and local and local DCT is basically doing DCT on patches, right? So you see that you see that it's dampening fast, and you see even if you cut here, you will lose much in FFT than if you than you would lose in DCT or wavelets. So I mean the best basis to use is it's also used in image compression. Like for example, JPEG uses DCT. They just apply it on the whole image, and then they do the cutting there, like quantization and stuff like that. So this is an important criteria to consider, which when you're defining a basis. So you want to truncate the basis at some point, and you don't want it to have too much information. So this is so the difference between DFT and DCT is, if you see, DFT is defined like this. XK is defined as X, capital X is a Fourier domain, and X is a time domain. So it's defined like this, and DCT is defined just the cosinus part, but it's a little different with this, some technicality, and there are different types of DCTs. The one we're using is called type 2 DCT. It's not too interesting, but they're used in different JPEG standards, so that's why they divided them like that. So if you look at the patches, so in DCT you don't have this the slant patches that you see in DFT. You don't have it in DCT. So apparently it's good for natural images. Apparently DCT captures natural images better than DFT. So why wouldn't they? I mean, wavelet transform is not. It's not just. You don't have a single matrix, and if you multiply, you don't get a wavelet transform. It takes much more time to compute. So of course that's why they don't use it in such operations, because it takes around 45 seconds to compute for 256 by 256. So it's tough to compute. So I mean it's expensive to compute, so they don't use it. So and JPEG, then DCT was it's apparently better for natural images. So that's the justification for doing it in transform domain. Like why do you want to use hard thresholding in transform domain? Is just so that DCT allows you. So hard thresholding is defined like this. So if you see, this is hard thresholding. If you remember, so soft thresholding was something like this, right? You have, I'll show you. Soft thresholding was this, and hard thresholding is essentially you don't even care about what your border is. It's just discontinuous, and it just puts 0 whatever is less than lambda and just cuts it off. But it's not relevant in this context, but just showing you the picture. Yeah. So yeah, so you get noisy patches. You apply this. This Rubik's cube means this forward transform of DCT, 3D DCT along this cube of patches, and then you do some thresholding and cut and keep only the top n percentile of frequencies or DCT coefficients, and you just and then you do an inverse transform and you get denoised images, right? So there are 2 steps. One each. So here, if you remember, in non-local means we were matching patches, but essentially we are filling only one value in the pixel, right? You're just getting the weights from this patches that you are forming. But in here, we instead replace the whole patch, and you get the patch estimates of you get the estimates from different patches in different regions. So you essentially at every pixel you vary it according to the importance of the patch. I'll go through it. So this is the collaborative filtering is basically you just I'll tell you how we fuse them, so then it will be clear. So essentially then you do it for several regions, and you keep placing the patches in this reference image, and you do it for all such patches. And you, of course, like in every like in non-local means, you define your search neighborhood, you define it, and it's expensive to search, so you can use a faster method like patch match. So yeah, so you do it for different locations in the image, and you place it and you place these patches, right? So this is the first step. So basically it has two stages. It's very technical, but essentially all the building blocks are pretty simple. It's just heavily engineered. So so you get such estimates out of all these replaced patches. And just a second. Okay, in the stage 2, instead of doing the hard thresholding, you just do the Wiener filter. You take it to some transform domain, apply Wiener filter on it, and then get rid of it. It's all technicality, nothing groundbreaking here. Just there's the fact that it works, right? Yeah. So how do you fuse? You get estimates of every pixel from different. Let's see in this image. For example, in this image, all these overlaps, you're getting different estimates of pixels from different neighborhoods, right? So how do you weigh them? So you define some goodness measure, which the goodness measure is basically how reliable is my estimate there. Is the estimate I'm getting there is. So basically it asks you to give higher rewards if your transform domain is sparse enough, when you're doing iterative hard thresholding. If your non-zero coefficients are high, then basically you're a little confused on where to put this if this value is right. So just give it less weight. And in Wiener filter, you just you have the weight of the filter, right? So you just weight it according to this filter, and then replace the whole patch according to this, right? So we get every patch gets and apparently this helps instead of just averaging them. The other thing you could have done is just if you get multiple values, just sum them up and average, right? Apparently this works much better than just doing averaging. So you get different values, then you fuse them somehow. Again, putting everything together, you have an image, you generate patches, and you pile them, and you do a DCT transform on this whole pile, and you apply hard thresholding, and then you take it back to real space, and then you distribute them where they came from, and you do the same thing for all the patch locations. So in the first stage you get some denoised result, and then you want to do additional step of this. They propose to do additional step of this applying Wiener filter on. So instead of doing hard thresholding, just do Wiener filter, and so you get here the input here is the output from the stage 2. So you take every patch and pile them up and 3D transform, Wiener filter, return it, denoise it, and put them back. And putting back is essentially just weigh them instead of just doing averaging. Just weigh them according to how many non-zeros they were, right? So all patches are not good. So summarizing it, basically it's so again I wrote some summarized everything in 2 sites, and so essentially you get it's the same thing what we talked right now, just in text. So it takes apparently it takes I used it, and it takes 8 seconds to run for 256 by 256 image, and also it was the state of the art. Like, it was competing with non-local means until 2014-15. Like, the first appearance of what people first did with neural networks was they just took patches and they put a fully connected network and they tried to train it, and it was as good as BM3D, and everybody was surprised. It was in 2012, but later people were able to beat BM3D using this ResNets. I mean, by ResNet I mean the skip connection. So essentially they were able to outperform this BM3D, and it's also extended to videos. For example, you can instead of matching local neighborhoods in 3D, you can just match 4D neighborhoods. I mean local neighborhoods in 2D, then you can match 3D neighborhoods in video, and then you pile all these 3D neighborhoods up, and then you take an average, hard thresholding, and yeah, and I think the most of the ideas here are taken from JPEG standard, JPEG 2000. So the idea of using DCT and matching patches together, it was proposed in like I think 2007, along with NLM, and it performs really well. Then do you have any questions in this? I don't want to finish soon. If not, then yeah, that's it.